Okay. Okay. So hi everyone. Welcome to another week, another Plan Talk. This week we're gonna have Juno Kim from University of Tokyo, talking about the paper Transformers Provably Solve Parity with efficiently with chain of thought. Please go ahead.
Okay, thank you for having me. My name is Juno Kim. I wrote this paper while I was a master's student at the University of Tokyo, but starting from this year, I'll be a PhD student at UC Berkeley. And this paper I wrote with my supervisor, then supervisor, Taiji Suzuki. And this paper was accepted to iClear this year as an oral presentation. So I'll present this paper, and at the end, if there's some time, I'll take a couple minutes and talk about a follow-up paper that we did and a line of follow-up works that we are right now working on. Anyway, so okay. So I guess you all know what chain of thought is, but as a very brief reminder, a chain of thought is when you prompt an LLM to solve complex tasks step by step by recursively generating intermediate reasoning steps to arrive at the final answer. And the whole like let's think step by step, let's take a step back and think about this type of prompts. But more recently, it's been observed, but not just prompting an LM, but actually directly fine tuning these models on ground truth chain of thought, and it greatly improves their multi-reasoning capability. So, for example, here we have an example where on the right hand we have a simple math problem. You have 5 tennis balls, you buy 2 more, and each can has 3 tennis balls, and you have to do a simple multiplication and addition. And instead of just telling the model to output the answer 27 or directly, uh, you want the model to like let's start with 5 balls, and then 2 times 3 is 6, and we add them to get 11, and so on. We have these like step by step like reasoning procedures. And so yeah, and more recently, it's been observed in not just generating one chain of thought, but for example, generating multiple chains of thought in parallel, and then kind of aggregating their responses by like best of n or majority voting, or even generating a tree of thought, like all possible like reasoning trees, and then finding the best uh, response by somehow searching through this tree using some search algorithm has been shown to further increase their these models' reasoning capabilities. So you have chain of thought, tree of thought, graph of thought, and all of these XOT variants. And now what people are doing is they're not just doing this at inference time, but they generate this like chain of thought or like tree of thoughts, and then they choose like a best chain of thought and say a suboptimal chain of thought, and they use these as like preference data to run some sort of like reinforcement learning algorithms like TPO, for example. And then they'll do that to like fine tune the base model, and they can kind of repeat this like in an iterative manner to continually improve these models. So like these types of works are what we're currently working on. But yeah, the original paper was just to study the benefits of a single chain of thought. Why is it better than just outputting the answer directly? So there's been a bunch of theoretical work aimed to understand these benefits. And one prominent line of work uh, uses complexity theory to evaluate the increased expressivity when using chain of thought. So basically, instead of trying to learn a single function in one go, what happens if you compose multiple functions? You're able to learn you're able to express a much larger function class, and that's been done uh, over a bunch of papers. Uh, the thing is, like these papers, they only talk about expressivity. They never talk about they cannot talk about like learning theoretic guarantees. Like for example, what function class can be learned with chain of thought? Can we actually like train these models to learn a wider class, for example? So, uh, and that's for good reason. It's very challenging to obtain computational guarantees for chain of thought type models because you have a model that's already complicated, like a transformer, and then you have to iterate that multiple times because what you're doing in chain of thought is you're basically taking your prompt, you're inputting it into the model. You get you predict the next token. You you kind of concatenate that into your current prompt, and you push it back into the model, and then you generate the next token and the next, and so on, because you're generating multiple steps, and then you get the final output. So your model in the end is kind of like a recursion of a complicated model. And then if you want to talk about like what this model can learn, say using gradient descent, then it becomes really complicated very quickly. Sorry, is this fine? I'm getting yes, this is fine. Anyway, so that's the problem that we wanted to address, is to look at what benefits are gained from a learning theory perspective when we use a chain of thought. And there's actually a concurrent work which studies a very similar problem. This paper by Win et al. They also study using chain of thought to learn also the parity problem. And they take a slightly different approach to ours, but the overall message is kind of similar. So I just wanted to point out that this is another very interesting concurrent work. But yeah, so our research question here is, how does optimizing transformers to explicitly generate chain of thought improve multi-step reasoning capability? This is not just like expressivity or say like what kind of functions can these like models approximate. Now we're talking about, we're given a function class that we want to learn. Can using chain of thought explicitly benefit these models in some, like, say, sample complexity or computational complexity sense? And in order to do this, we take a very, very simple model to study, and that's the parity problem. And we'll get into the details in just a moment, but existing theory basically tells us that parity is very difficult to learn for any gradient-based algorithm like gradient descent. Basically, you need exponential samples or exponential runtime, and that's why we want to study parity as like this difficult multi-step problem. And basically, we want to show that by using a chain of thought scheme, a very simple transform model can learn this very efficiently. So we show that by using some sort of like teacher forcing or self-consistency scheme, chain of thought can learn this much more efficiently than like any gradient-based algorithm can. Okay, so what is this k-parity problem? Basically, you have d-bit inputs. Here we have x1 to xd. These d bits are all either +1 or -1. And then we have a size k subset denoted by p, which is just a subset of the indices from 1 to d. And then the function that we want to learn, y equals px, is just the product of the bits at those positions. So the example in the picture above, here we have d equals 6. We have 6 bits, where the columns are the different bits, and each row is a sample. And here we have 3 columns outlined in red. This is the size 3 subset. Here we have x1, x4, and x6. So the function that we want to learn, y equals the product of x1, x4, and x6 for all of these samples. So it's a very simple like multiplication or like plus minus problem. But this is actually very difficult to learn in the following sense. There's this theory, the SQ theory or statistical query theory, which basically tells us that when k is on the order of d, any gradient-based algorithm requires exponential queries or exponential precision. That means exponential samples or runtime to solve this problem. And I won't get into too much details because this is quite technical. But here, any gradient-based algorithm means that any algorithm that, let's say, f theta is your model, where theta is your parameters. And you can define a loss function that depends on theta as the average of the squared loss of your model. Basically, you sum over y minus f theta x squared. And your algorithm is only allowed to compute the gradient of your loss, nabla L theta. And you can do this, say, n times. Sorry, n is the number of samples. You can do this t times. And you can update your algorithm or you can update your model however you want, only based on the information gained from these queries. And the problem is you want to solve parity in the sense that you want to figure out which of the bits are being multiplied. And furthermore, you want to be able to predict the output from for any new input x. And basically, the theory tells us that you cannot do this unless either n, the number of samples, or t, the number of queries to this loss function, is exponential. And since d is the dimension of your model, which becomes very large very quickly, it's infeasible to learn using gradient descent, is basically the conclusion. Now, this theory is quite classical. It's been around for decades. But this is kind of heuristic in the sense that there's a non-rigorous like jump from this like precision to sample complexity argument. In our paper we do make this rigorous. So let's just briefly look at the theorem. So this is kind of a strengthened version of the existing heuristic theory. And basically, we show that if n is exponentially large in the dimension, then there exists an oracle such that any iterative gradient-based algorithm, which makes at least polynomially many queries to nabla L, cannot learn parity, which basically means that the expectation of your L2 loss will always be very large, or like it cannot go below, say, 1/2. That's the part 1 of this theorem. Part 2 is basically for the polynomial sample size. Let's just skip that. The main takeaway is that any algorithm which can only query gradients of this end-to-end loss cannot solve parity efficiently. Let's just skip this sketch for now. Yeah. Okay. And then the main contribution of our paper is that actually you can solve parity efficiently if you just use a chain of thought scheme. But what is chain of thought in this like very simple like plus minus parity problem setting? The idea is that you can decompose parity into smaller 2-parity subtasks. Here, when I say 2-parity or k-parity, k is the number of bits that are being multiplied. So you can see in this, the figure displayed on the screen is like an 8-parity problem. So you have 16 bits, here d equals 16, you have inputs x1 to x16, and then you're multiplying 8 of those bits. So here you're multiplying x1, x4, x6, 7, 8, 12, 13, and 15. So you want to learn an 8-parity function. Now, instead of learning this in one go, the idea is that you can basically learn to multiply 2 at a time. So here, x17 on the second layer of this tree is multiplying x1 and x4. And x18 is multiplying x6 and x7, and so on and so forth. So you have x19, x20, and then on the second layer, you have, or third layer, you have x21, which is the product of x17 and x18, and x22, which is the product of x19 and x20. Finally, on the uppermost layer, you have x23, which is the product of x21 and x32, and you can see that x23 is multiplying all the 8 bits that we wanted to multiply, and that's our desired output y. And so the idea is that we can decompose parity into these like 2-parity smaller problems, and each of these 2-parity subtasks should be easy to learn, because if you recall for a moment the negative result that we showed using SQ theory, this assumes that k is on the order of d. But if k is, say, 2 or 3, then it should be much easier to learn. Okay, so each of these 2-parity subtasks should be easier to learn, and then we only need to solve, let's say, k minus 1 of these in parallel in order to get to the final y value that we want. So this should be much easier to solve. And now the question is, can we do this with a single fixed model? Because as in chain of thought, we have a single model, the LLM, which is generating the next token, which is predicting the next token like 1 token at a time, and you repeat this until you get the desired output. So you want to study whether a fixed model can learn to generate all of these intermediate values, say x17 to x23, in order when we recursively take its output and push it back into its input and repeat that. All right, is everyone with me so far? Okay. And so what's this model? This is a very simple 1-layer transform model, actually. Since the problem of parity is very simple, we only need to consider a 1-layer transform. And even for this very simple model, we can already solve a separation with the negative result we had earlier. Okay, so what does this transform look like? So this transform will take as input the d bit tokens that were our provided input samples, x1 to xd. So you can see that so we set up this in a kind of non-trivial way. So you can see that the rows here in this diagram are the samples, and the columns x1 to xd are the bits of these samples. So each input token will have n bits corresponding to the n samples. And we also have dummy tokens, xd plus 1 all the way to xd plus k minus 1, which is, in this tree, that's x23, which is the final output y. So we have a bunch of dummy tokens that should learn to generate these intermediate tokens, but in the beginning, we don't know anything, so they're all 0. They're all set to all zeros. And then to all these tokens, we also append one hot positional encoding. The positional encoding is basically because what this model needs to learn is to, for each node, say in this diagram, you're looking at, say, XM, it needs to know which two tokens it's computing the two parity of. So going back to this tree, basically, say for X17, the weights corresponding to X17 need to know to look at X1 and X4, these two bits that it needs to compute the product of, and none of the other bits. So basically, we want the model to learn this tree in its attention weights. Right. And we do this by parameterizing the softness layer in a very simple manner. We combine the key and query matrices into a single matrix W, and the entries of W will basically encode how much each weight is looking at the weight below it. We also fix the value matrix to the identity, just for like simplicity of analysis. And we'll also have a feed-forward layer, which will also be fixed, again, for simplicity. And it needs to be fixed to a link function phi, which sends 0 to -1 and plus -1 to 1. So why it needs to do this is that basically, if you look at the computation the transformer is doing, now you can see that if you write the input tokens as x1 to all the way to xd plus k minus 1, the transformer will be computing x1 hat to xd plus k minus 1 hat, where the original d bits, we assume the original input x1 to xd bits are unchanged because that's just the input. And then all the intermediate bits will be computed as follows. The equation below, it's kind of complicated, but if you look at it, it's just the softmax computation. So it'll be computing a weighted sum of all the previous tokens, and the weights will look like this sigma j wm factor here. This is just your softmax computation of the weights. And because of the way we set up this model, basically, we make the attention scores only depend on the positional encoding parts, not the token parts. So each entry of the attention layer will actually just be representing the strength of each position, each dummy token position, and how much it needs to look at each token that comes before it. The model is autoregressive. So for example, x21 here can only look at all tokens from x1 to x20. So it's computing a weighted sum of all tokens from x1 to x20. And in the beginning, they'll all be uniform. But we want, we want after training for x21 to be able to zoom in or focus only on its child nodes, which are x17 and x18. So it should be computing the average of these two tokens. And since we had this fixed link function, that sends 0 to -1 and plus -1 to 1. What this is doing is if the two child tokens were, say, +1 and +1, or -1 and -1, then the average will be either +1 or -1, which will be converted to 1 due to this link function. So basically, it will be computing the parity of these two bits. And if the two tokens are +1 and -1, or -1 and +1, then its average is 0, which will be sent to -1. So indeed, this will convert the sum or average to the parity. So sorry if this is kind of complicated. Basically, we set up this model so that once the attention layer learns this tree structure, the forward pass will just be computing each of these two parities at one time. And so we start from the values from x1 to xd, and then if you apply this transformer, let's look at this tree again. If you apply this transformer, the values for x17 to x20 will be updated with the correct values, assuming the model is learned. But everything above it will not have been trained yet. So we take its output, plug it back into its input, and next time around, the values for x21 and x22 will become fixed because the model is autoregressive. And then if you take this output and plug it back into input one more time, the final layer x23 will be the final value will be computed, and then we will take its output y as the final output as the model answer. So the model is literally doing this computation one step at a time. Okay. So that's our transformer model setup. Yeah. And so how do we train this model? So we'll consider two modes of training. The first one is teacher forcing. So teacher forcing is where you train a transformer, say, or an RNN, or like any autoregressive model by inputting the ground truth labels at every step when you're predicting each new token during training time. So for example, let's look at this image here. Say you're trying to predict a sentence like 2 people are running. So you start with the start token. The model predicts 2, which is correct. That's fine. Then you take its output and plug it back into its input. So and then the model predicts the next token, which is birds. Sorry, which should be people. But say the model predicts something wrong, which is birds. So that's wrong, and that will increase your loss, of course. But when you're generating the next token, you don't take this wrong token, birds. You give the model the correct token, people, and make it predict the next token. So at every step, you're giving the model the ground truth up to the model, the token that you're predicting. And as you can expect, this prevents error from accumulating because each time you're giving the truth, the ground truth. And okay, so that's the way so that's how we generate each intermediate value, and then we sum the loss over all intermediate states. So this is our chain of thought loss. We sum the loss from index d plus 1 to d plus k minus 1 because the first d tokens are fixed. And then we do gradient descent on this loss. So one question you might have is, why don't we just train on the output loss? Basically y hat minus y squared. And the answer is, if we train on y on just the output loss, then this negative result that we discussed earlier will come into play, because this applies to any gradient-based algorithm, like chain of thought, or like any classifier, or any like CNN, or whatever you use. This negative result will apply, and you won't be able to learn the parity problem. So that's why we consider this chain of thought loss, which sums the error over all the intermediate states, and that's how we can get a separation. Anyway, so by training with this loss, we can show the following results, which basically says that if the number of samples n is at least or about approximately d squared, and we use any approximate oracle. Here we use the approximate oracle to be able to contrast with the SQ result. It's not very important, but yeah, basically we only need d squared samples, and then for any target parity, just one step of gradient descent, basically here W1 is just one step of gradient descent applied to the initialization, W0, which is just the zero matrix, with a specific learning rate, eta. This one step update will immediately achieve test loss, which is like O of d to the minus, let's say, epsilon over a. Epsilon is here, like how many samples you have over d squared. Basically, you can achieve let's say little o of 1 test loss. So basically, you can solve parity with just one gradient step. Okay, this is fine. If you have any questions, feel free to just interrupt me. But yeah, so going back to the negative result, which says that you need either exponential samples or exponential runtime, exponential updates. Here we show that with this chain of thought loss, you only need d squared samples and only a single gradient step. And how to do this is basically we want to compute the gradient descent dynamics of our transform model under this chain of thought loss. And basically, this whole teacher forcing scheme is basically decomposing your learning problem into all of these little two-parity problems. So yeah, you end up solving every two-parity subtask at once, and each parity subtask can be solved with a single gradient step. You can show this by just computing the gradient of your loss function at initialization, and then computing all the interaction terms. And then you can show that the leading term of gradient is large on the order of like 1 over d squared. For the parameters which correspond to the branches of this tree that we want to learn, and any other connections will have much smaller gradients. So you just take one gradient step, and all of these connections that we want to learn will immediately be reinforced, and we will be able to recover this tree very efficiently. So that's our first positive result. Now this is slightly cheating in the sense that teacher forcing explicitly breaks down your problem into all of these small one-step problems. So it's actually not very interesting because true parity is like very easy to solve. The more interesting setup is when you do not have teacher forcing. And why do we consider this setup? It's because when we actually train transformers, teacher forcing is known to induce like exposure bias or distribution shift. Because at training time, you're only showing the model like ground truth fragments of your chain of thought, and it only needs to generate one step at a time. Whereas during inference time, the model will have to kind of generate the entire chain of thought in one go by itself. And then once it has even a small bit of error in its generation, it will accumulate very quickly and kind of blow up exponentially. And it's the model will not be used to this because it's not trained on that sort of like erroneous data. So in practice, people kind of mix teacher forcing and non-teacher forcing. And here we'll consider the case where we do not have any teacher forcing. Basically, we're not allowed to look at the ground truths during the generation of the training space, and the ground truth values only appear in the loss function. Yeah. Basically, in this like two people running example we had before, say the model generated 2 correctly, but then it changed the people to birds. The model when the model is predicting the next token, it will have to deal with this error. It will have to start with 2 birds, and then the model will generate flying instead of running because birds don't run. And then the error will kind of blow up. So you can imagine that this dynamics becomes complicated very quickly, not just in practice, even in theory, because once you have a small error and you kind of repeat even if you have a very small error, if you recurse a function enough times, the error will kind of blow up very quickly. So we deal this by adding a couple of modifications to our transformer architecture, which we hope also kind of corresponds to what happens in real life. So we have 3 modifications. The first one is quantization. We will be rounding all weights to the nearest integer after the gradient update. And this will kind of help stabilize the error. And of course, this corresponds to LLM weight quantization. We also will impose a stronger autoregressivity where each token is only allowed to depend on previous levels of the tree. So if you remember this tree structure we had from before, for teacher forcing, let's say, for example, x22 was allowed to look at all tokens from x1 to x up to x21, so everything that came before it. But now we only allow x22 to be able to look at all tokens from x1 to x20. So everything on the previous level, everything on the previous level, but not the tokens on the same level. So this is just a slightly stronger version of the autoregressivity causal mask. Not quite sure what this corresponds to in real life, but yeah, this will help simplify the dynamics a lot. Basically, instead of having to, let's say, recurse the model k times or k minus 1 times, you only have to recurse the model log k times because you have to generate each level at a time. And then that will kind of reduce the number of times you have to recurse the model. So I guess that could be taken as like a very simple, if your chain of thought is shorter, then you will have less error propagation, which is kind of intuitive. And finally, the most important modification that we do is a sort of self-consistency scheme. And this will filter for faulty reasoning. In the following sense, when we're kind of computing the forward path of the model, and at some point the model starts outputting garbage, like if the output token is like all 0 or all +1 or all -1. If tokens on some level become uninformative in that sense, we will zero out its output and just not compute the gradients from all tokens that come after it. So this is similar to what we actually do in chain of thought. We do self-consistency and try to verify each step of a chain of thought, say with an external model, for example. And if the generation is too faulty, then we kind of discard the chain of thought. And here, if we do this kind of simple filtering scheme, this will induce some sort of curriculum learning where we will have to, the model is forced to learn each level of the tree, like one level at a time. So the model will be forced to kind of focus on learning the first level of the tree, basically the first connections here, before being able to unlock the next level. So once the connections for the first level are learned, then the model will be able to proceed to the next level and so on. So it will induce this kind of like level by level curriculum or step-by-step learning. Anyway, now with these modifications and with the same chain of thought loss we had from before, where here, so the loss looks exactly the same, but here the estimates x hat must come from iterating the model until the model fills out all the intermediate tokens by itself, and then we take those as our estimates. Whereas in teacher forcing, for each token, we were allowed to give the model all the ground truth tokens leading up to it. So that's why it's a different loss function. But with this loss function and with these modifications that we had, we can actually show that the model will achieve a vanishing test loss with log k iterations this time. And the number of samples n is the same. It needs at least d square samples. And the model will achieve vanishing test loss. So it will have solved the parity problem. And again, this, similar to before, this holds for any target parity. So just one caveat is that this SQ result that we have from before, this kind of holds with high probability over your target parity. So this negative result is considering the target parity itself also as a random variable, because you have d bits, and then each parity problem is determined by choosing k of those bits to multiply. So you have a total of d choose k different possible parity functions, and this whole difficulty result can be interpreted as d choose k is exponentially large in d as soon as k is like on the order of d. So to be able to like figure out which is the true function will require exponentially large compute. Whereas in this positive theorem, we show that we only need d square samples and log k, basically order of log d iterations. Suffices the chain of thought, even without teacher forcing. Okay, and this holds for any target parity. Right, so we have this kind of separation between ordinary gradient-based learning and learning with this chain of thought loss, where we try to learn these intermediate steps. It kind of breaks down this difficult d choose k problem into separate d choose 2 problems, 2 parity problems, and in the end, it brings down the whole like learning theoretic complexity of this problem. So I guess how we obtain this separation is very intuitive, but the interesting part is that we show that this is possible with a very simple single layer transform model. Okay. And we also have some experiments that back up our theory. So we kind of use the same setup. We choose d equals 64, so all the bit inputs are 64-bit plus minus ones, and then we choose k equals 32. So we're multiplying 32 out of those 64 bits. And so if you just want to learn a single parity function, that's 64 choose 32 possible combinations, which is very large. So so we consider 4 different trading schemes. The red line here. So the left diagram is the chain of thought loss, and the right diagram is the target, or the loss computed on only the prediction y. And we study 4 models. The red line is the end-to-end model. So we just train a single layer transformer on the target loss, and you can show that it doesn't move at all. It fails to learn anything, as the negative result predicts. And then we consider 3 different chain of thought schemes, and so the blue line is the chain of thought with teacher forcing, and you can see that it actually manages to learn this parity problem quite efficiently. So the only difference between this experimental setup and our theoretical setup is that here we consider a realistic learning rate. So for our positive results, we actually need a very specific learning rate in order for this problem to solve, to cleanly solve each two-parity problem with one update. Whereas in reality, we need to use a more realistic small learning rate. But we're basically showing that even in this more realistic setup, our theoretical results kind of, you can see that the teacher forcing scheme is able to learn this chain of thought loss in a very linear fashion. So if you look at the left diagram, the loss goes down very predictably, and if you look at the right diagram, the loss actually slightly goes up before falling down very quickly. Now, why this happens is that you're basically learning the connections of this tree, and the connections will become stronger and stronger over time. But if the connections haven't fully been like resolved yet, in the sense that so you want each of your branches to be like 1/2, the weights need to be 1/2, and everything else needs to be 0. But unless you actually achieve this with very high precision, at inference time the error will accumulate very quickly, and then your result will still be garbage. So if you want to achieve 0 target loss, the model needs to be really solve this tree parity problem with very high precision, and that's what happens at around 150 epochs. Anyway, that's the teacher forcing scheme, which is very predictable. And the more interesting thing is this green line, which is the chain of thought without teacher forcing, but with our modifications, our self-consistency scheme. And you can actually see that this model does this kind of step-by-step learning, has this step-by-step learning behavior. So you can see that the model has this kind of initial plateau where the model is resolving each layer of this parity tree. And then once it kind of resolves one layer, the loss drops down dramatically. And then you enter the next loss where the model unlocks the next level and then starts to resolve that. And you have 1, 2, 3, 4, 5 different regimes because you have k equals 32, which is 2 to the power of 5, so you have 5 different levels. So you can actually show that this loss goes down like one step at a time, corresponding to each level of a tree. And if you look at the right side, it doesn't actually go down until the very last step, and that's for the same reason. Unless you have fully resolved the entire tree, the final output will still be garbage. So you kind of have to wait until all of the levels have been unlocked for the loss to go down. So that's what happens at around 270 epochs here. So we verified that this consistency modifications actually help the model learn step by step. To kind of reinforce this point, we also studied chain of thought without teacher forcing and without our like consistency modifications, and that's the yellow line here. So if you look at the diagram on the left, the yellow line also seems to be doing this kind of step-by-step learning at the beginning. You can see that it has these kind of wobbles that go down initially, but the model ends up kind of failing to learn the full problem. Around 150 epochs, you can see that the model starts fluctuating because the error builds up too much. And you could argue, just by looking at the left diagram, you could argue that, well, the loss still goes down to quite a small level, so isn't that okay? But if you look at the right side, actually the yellow line never dips below this 0.5 loss, which is the trivial loss. 0.5 is what you get if the model always outputs 0, so it's the trivial loss. And the model never goes down because, again, if you haven't resolved the full tree, the output will be garbage. So we've actually shown that you need either teacher forcing or this step-by-step like consistency or step modification to stabilize your training in order to solve the final problem. And that it fits our positive theoretical results quite nicely. Right. So the main takeaways is that training explicitly for chain of thought generation here explicitly means that you're not training on your end-to-end loss. You're training to predict each step of your chain of thought. That's our chain of thought loss. And by optimizing with the chain of thought loss instead of the end-to-end loss can provably improve performance on the parity task. And moreover, you need to control the error accumulation by either using teacher forcing or using some self-consistency like modifications to ensure you have this effective step-by-step learning scheme and do not have too much error buildup. So yeah, that's our two main takeaways. Right. Okay. So that's the end of the chain of thought paper. If you have any questions, feel free to ask. Is it okay if I spend a couple minutes talking about the follow-up paper that we did?
Yeah, I think we have a few minutes. There's still going to be then time for some discussion.
Yeah. Okay. Yeah, that would be great. Okay, so this paper, in the end, what we're talking about is it better to do chain of thought versus no chain of thought, and why is it better? So we've obtained this theoretical separation versus any gradient-based algorithm without chain of thought. Trying to solve parity end to end must require exponential compute, but a very simple transform model using chain of thought loss can solve this model can solve this problem very efficiently. So we've basically showed the importance of chain of thought on a simple multi-step task. But now the question we want to ask is it better to do just one chain of thought or generate, say, a tree of thought, for example, and then do some sort of complex search routine over this tree? Because I mentioned at the beginning that nowadays models are not just generating one or two or a bunch of parallel chain of thoughts. We're generating like multiple different paths and then trying to kind of find the best path using, say, a process reward model or your verifier or whatnot. And this whole like test time scaling business. And we want to show that we want to study when this helps. So yeah, basically we have this whole plethora of post-training paradigms now, like supervised fine training, RLHF, purpose optimization, so on. And it's been shown that like these kind of post-training paradigms can drastically improve your reasoning capability by just kind of increasing your reasoning efficiency, say. Given a fixed task, given a fixed inference time compute budget, you kind of want to do some sort of search over your possible chain of thought generation space. And then this not only allows you to improve the output of your model, but then the search trace can be utilized to fine-tune the pre-trained model, or even distill the reasoning traces of a more powerful model into smaller, more efficient models. And so we wanted to study how can the benefits of test time scaling for chain of thought be rigorously understood. Yeah, sorry. So this is a paper with Taiji and also Denny and Jason. And this is a paper that we will present in ICML in a couple of weeks. And very briefly put, we propose a very simplified model of chain of thought reasoning. We model chain of thought generation as a Markov chain, which is a very simplified assumption. But yeah, so we view the space of all possible reasoning states as some sort of abstract Markov chain, as an abstract state space over which chain of thought is basically doing something like a Markov chain. And in this model, we distinguish between easy or trivial reasoning steps, for example, like rearranging terms in an equation, like doing very simple arithmetic manipulations, and hard or crucial reasoning steps, say like applying an abstract theorem to your like assumptions to generate a mathematical proof. And we want to know, can the reasoning, can these like hard steps be somehow found or boosted using these test time inference schemes? And can we use that to understand the benefits of test time scaling? So the task is a path finding task. You're given two nodes, x in and x out, and you want to find a path from x in to x out. So that's one formulation of a potential like reasoning problem. So so we have clusters formed from these easy or trivial reasoning steps, and we have hard steps, which are like cluster transitions between these clusters. And we assume that these are low probability edges. Basically, these are these hard steps the base model will have a hard time generating. So, and this whole kind of cluster structure can be modeled using metastable dynamics, which is commonly used in physics. But we take these tools to study, the healing times of Markov chains on this model. And then we actually show we can obtain like tight bounds for hitting times with this model, and we show that by using some search procedure, the model can actually find these hard steps and boost their probabilities, and in turn that will improve your hitting. That will bring down your hitting time, the time to solve your pathfinding task. And there's two things you can do with these search traces. You can boost these the probabilities of these transition edges using RL. We consider PPO, and then we show that these edges probably can be boosted, and that will improve your hitting time. Another application is that the model can learn this cluster structure and then distill this structure into a smaller model, which only needs to memorize this like higher level cluster structure. It doesn't need to like memorize the exact structure inside clusters. It only needs to remember where the hard nodes are, where the hard transition edges are between clusters. And by doing this kind of distillation process, we show that the resulting smaller model can find paths between tokens very efficiently. And we also show another like SQ theoretic like lower bound, which shows that doing no search or a simplistic local search can fail to solve this pathfinding task. So the main takeaways is basically we can model easy versus hard tasks using this Markov chain model. And then from this model, we can derive exact hitting times and then show that running search and either boosting these hard edges using RL or distilling this overall cluster structure into a smaller model can both help make this pathfinding task easier to solve. So that's the benefits. That's some possible benefits of test time scaling. All right, and yeah, so we're continuing to work on theoretical understandings of benefits of test time scaling and search and process reward versus outcome reward and everything. So if you're interested, please take a look at our paper, or you can contact me via this QR code. Okay, and I think that's it for the presentation. Thank you for listening, and then I guess we'll take some questions.